we'll start to look into what is computer vision. We'll after compare like how is computer vision different from human vision? How can we differentiate, or what are the similarities? There could be some similarities between how we perceive an image and how does a computer perceive an image. So we'll look into that. Then we'll get into the dirty part of computer vision, which is maths. And I have tried to make it as simple as possible, and we can look into that during that part. Then we'll look into some convolutional neural networks, which is such as LayNet or AlexNet, ResNet, and different architectures that were built to solve the computer vision problems. Then we'll move into applications of computer vision, which we'll see like what are the recent trends in which what are the applications, like real world applications of computer vision. And we can also look at, and after that, after the break, we'll move on to hands-on session. So this is the schematic that we'll be following today. So let us begin with what is computer vision. Basically, what is computer vision is it enables computer to derive meaningful information from digital images, videos, and other visual inputs. Is it visible at back? Is it fine? Yeah. So what we can understand is this is like, okay, we need, if a machine wants to work in an environment, the machine needs to know what is its environment looks like. That is the thing that computer vision tries to solve. And AI enables computers to think. Computer vision enables them to see, observe, and understand. How will machine know like what is the distance between two objects? What is this object? How can it differentiate between a cat and a dog? Without looking, no one can differentiate until unless it hears the voice. If we exclude that, there is no other way to differentiate between cat and dog, other than using computer vision. And computer vision is used in many industries ranging from energy and utilities to manufacturing, automotive, and the market of this is growing exponentially. There's a whole new market. There are many industries that have been replaced with this computer vision, manufacturing, robotic arms, and all these technology and artificial intelligence machinery. So this is what, in a nutshell, what a computer vision does and what a computer vision is. So moving on, what is human, like how does it differentiate between human vision and computer vision? So as human, it's like going into human vision, it takes little bit of biology to understand. It's like how we see an image is through light. If there's an object in the dark, we are not able to see that object until unless some light is given to that image. Then only our brain receives that signal. Okay, there's this light coming from that image. So this could be some image or some object. So this is how human vision works. Human perceive things as they are and retain what they recognize, storing it deep in the brain until they come across those things again. So once we see a cat, we remember what a cat looks like. It's small, it's furry, and all these details, it is remembered and kept in our mind. And human vision is about how I detect light patterns and coordinate with the brain to translate light into images. Like this is the point that I said, like it detects light patterns and it tries to understand what that object is. So following on, human recognize objects effortlessly and have no problem describing object in a scene. So if I see a scenario in which there's a mountain, there's a river, there's there are birds flying over there. So as a human, you can recognize those things and you are able to differentiate those things too. But how is this different from computer vision? Like how do computer get those vision and how does it look? How does it get to know what an image is? So if we look at an image A, as a human, we have been studying this since our class, like nursery class, like what a A looks like. We are not being taught like this, okay, it's in the binary form, it's in the matrix form. We are taught in that way, like what a A looks like. And whereas in computer vision allows computer to sense their surrounding and identify things similar to how humans perceive. This is one similarity between computer vision and human vision. Both of them are similar, like in what like what is the use, like surrounding, identifying what is in their surrounding and what is in their environment. So that is what computer vision and human vision has similarity in. So computer vision uses machine learning techniques and algorithm to identify, distinguish and classify objects. So in human vision, it was our brain who was receiving those details and trying to understand what that object was. But whereas in computer vision, it is the machine learning techniques and algorithm which helps us to identify, distinguish and classify the objects. Moving on, object recognition is one of the most challenging problem in computer vision. Like I said, like as human, we are able to easily, comparatively, we can easily recognize objects other than computer vision. We can look into like computer vision, like object recognition is a tough and a challenging problem in computer vision. So we need to overcome that problem. So we'll look into how can we overcome that problem. So in yesterday's hands-on session, we saw like I drew this matrix, like how an image is represented. So over here, A is transformed into a matrix. It could be 5 into 5 matrix, 10 into 10 matrix. It could be any matrix size, and that matrix is converted into a binary, grayscale, or RGB. It could be in any format. But over here, if you try to understand from the matrix, you can leave out the image part. If you try, you can see somehow it looks like A in that matrix. So from that, the computer tries to understand, okay, there's this pattern which is matching for A. Like there's a two slanting line, there's a horizontal line. In that pattern, it tries to understand, okay, it is A written over here. So this is the basic difference between computer vision and human vision. So moving on to, we can see an example of like, okay, this is a detailed example. As a human, we know that is what is it? A flower. We know that. But how do we know that? It's kind of cheating because from evolution, we have stored those information in our brain, okay, that is a flower. We are not using any other method to understand, okay, this is not a flower or this is a flower. We can easily understand that's a flower just by looking into it. But for our part, we have been training and due to evolution, we know that it is a flower and the information is stored in our brain. But since computer is seeing it for first time, so it is the matrix representation which it will see and which it will try to understand from. So that this is how the computer will look. This is how the flower will be represented in a computer vision statement or problem. So we can look into detail, So this, so the intensities of this matrix is from 0 to 255. It is from different, since it's an RGB color, it could be in different intensities, and it is in this format how the flower is being represented in the pattern. So let me just show you, like over here you can see these are dark colors, these are light intensities. So you can see the difference between the intensities, like over here it's only 7, 14, since 0 is the white color and the dark is 255. So in that format we can look, it's like 7, 14, 16, and there's a huge transition between white and dark color. So this is how computer tries to understand what the flower looks like. So finally it tries to understand the pattern from that matrix. Okay, this is what flower should look like. And now if it counters any other image, similar image with similar matrix or similar pattern, it tries to learn from it. And it is finally able to tell us that, okay, this is what flower looks like. And this is how it is represented in a computer vision. So computer vision, it's like similarly I said earlier also that object detection and classification is one of the challenging tasks. For us human also, it could be something sometimes tedious. So I would like to give you one example. This is one of the famous example, which is this thing. So as human also needs some kind of focus to differentiate between a breed of dog and a muffin. Most of them, you think, if you look like, most of them are similar. If you just, as human, we know we can differentiate a little bit. But this is how we try to confuse computer vision. But at the end, computer vision still gets a better performance and a better or equal performance as human. But how does this happen? This is using the power of computer vision and convolutional neural networks that will look in further slides. So this is what I wanted to give an example. Like, it's not that easy to identify and classify images. It could be difficult. Like maybe you can guess all of them, but maybe some of you couldn't. Just maybe you can look into the first and the second image itself. It looks so similar. Finding difference between them is a difficult task. And there's one more example, a sheepdog and a mob. This is one more example, like how we try to confuse computer vision, how we try to challenge computer vision. Like, does it understand how we want it to understand? Is it able to classify mob and sheepdog with an accuracy? This is what the problem statement is actually. Like, we need to teach the computer vision to look properly and to classify in an environment and surrounding with a better and best accuracy that they can give. So this is one more example that I wanted to add, was like sheepdog and mob, which has similar characteristics and features, not features, but it looks similar. So moving on. So okay, I want to just, it's like we can't skip the maths part. It's the hard truth. It's like we need to know the maths part, and the goal is not to make you remember those formulas, but to provide you with the intuition of what is happening underneath. This is the most. It could be for some of us or some of you. It could be the most boring part, but I've tried to make it less boring. And don't be discouraged if you are not comfortable with linear algebra and differential calculus. These are the topics that is the must, like basic. These are the fundamental building blocks of computer vision, CNN, deep learning. It's okay if you don't know, but to get the best and the better understanding, you are required to know this linear algebra and differential calculus. But at this stage, you are not required. For further down the career, or if you want to pursue this, it is the must or it is required to know this maths. So let us start. I've mostly tried to skip the maths part, but so we have seen this yesterday. Okay, I've made similar representation over here. You can see there's an x. In this image, we can see x is, what is our x? Can anyone say that? X is our input. And what is the next layer that we have? It could be like hidden layer. In a deep learning, there are mostly the input layer, hidden layer, and output layer. So hidden layer can be n numbers of hidden layer. It doesn't matter. There could be n number of output probabilities. That also doesn't matter. And input also doesn't matter. But what it has to be consistent with is x input, hidden layer, and output. So over here we can see what is this like circle things are perceptron, and the perceptron connecting to another perceptron is this, what we say, a connection that transfers the data from one perceptron to another perceptron. So this is somewhat neural network that you must have seen yesterday also, in yesterday's hands-on session and theory part both. And this is what densely connected neural network architecture is. Like, some inputs is given with some weights and bias is added to it. It does some mathematical calculation, that is Wx plus b. Further, it tries to calculate in each and every step, it calculates Wx plus b. And further, it gives an output probability, or either in this case, there's only one output, so it is trying to output a single class. So this is what neural network looks like. But now we will see how is it different from, actually it's a subset of, computer vision is a subset of deep learning. And we will see how deep learning is incorporated in computer vision and CNNs. So I've talked about this. Okay, this is the most important part. If you don't know how data is being manipulated, how data is being changed, so you can't go further in building model and building and training model. So this is how actually a data is represented. Let us take an example over here. It's black and white image. We are simply taking black as 0, white as 255 as our intensity. And if you see the matrix, you can see that it is forming a shape of 9 in matrix. And this is us human, we can look at an image and we can say, okay, and classify it's a 9. But this is how an image will be passed through a model in a matrix format. Since it's a black image and it's what do you say? It has only one channel, which is black image, black or grayscale image. But there could be multiple channels, such as RBG. You know, red, blue, green images, like colorful images. Those are in RBG format, and those have 3 channels, and each channel has their own intensities. Each matrix has its own intensity of red, green, and blue. This is how the data is being given as an input to the model. So this is the digital photo data structure, like how this is the data structure, how photo is built in computer vision. It's simply in the form of matrix. So are we clear till here? Is there any issue like how is this matrix being built? How is this being calculated? And that we'll see further. But till here, if everyone is clear, we can move forward. Okay? Okay, fine. Yeah. So those who don't like maths can skip the bottom part. No need. It's like, and those who are interested in maths, I'll just tell them briefly what it is. It depends. So we'll move to convolution. So it is a process where we take a small matrix of number, we pass it over image and transform it based on the value from filter. So okay, let me go to the next slide first, where I've given an animation. Yeah, from this you can understand better how this convolution is actually working. You are given an input image over there. It could be anything. It could be like, it could be 10, 10, 10, 10, 0. It could be in any image. And what is this kernel? It's a filter. Okay, what a filter is, it's applied on the image to do the convolution matrices. So what we do is we take the input image and we pass the kernel. What is kernel? Kernel could be any filter. It could be, okay, just let me go to next 1 second. This would give a better, I'll just keep on going back. So, okay, this could be one kernel. What is this matrix? It tries to identify a filter in it. So if you are given an image over here, you can see, there is an RBG image. In that it is able to class, if this is an image, and there is one filter over there which recognizes all the horizontal line in an image. Then the next filter that is being applied is it understands all the vertical image. So similarly, we can build multiple filters to identify like what is there in an image. So what is the building blocks? It could be multiple horizontal line, vertical line, cross line, and different filters that could be applied to understand what the pattern of the image is. From that matrix, it is trying to understand like what is the pattern in the image, and that is the input that will be given to the model to for its better understanding and giving us better accuracy. So I'll go one slide back. So now you can understand like if that was our input image and some convolution. Convolution is a formula, like it's a formula that, or you can say it's an operation that happens. You can go deep into math. I'll just go back into it. So there's this kernel. Kernel is the filter that I'm talking about. Either it's kernel or filter, it's both the same thing. So it kind of slides into an image and it tries to build a feature map. It tries to extract a feature from the input image. You can see over there, like from kernel, it's doing some operation using convolution and it's trying to generate a feature map, which it is getting from the input image. Similarly, down the architecture, it will do the similar. It will find pattern, keep on finding pattern until it can find a solid pattern to identify or match a certain object. So this is what convolution. This is the first step that happens in a convolution neural network, and one of the major steps. So where the input image is denoted by F, our kernel by H, Okay, this is the formula. What is F? F is our input image. H is our kernel, which is the filter. M and N is the height and width of the matrix or the input image which is given. So after placing our filter over a selected pixel, we take each value from the kernel and multiply them in pairs with corresponding values from the image. Finally, we sum up everything and put the result in the right place in the output feature map. This is the same thing that was happening during that animation. It was just trying to slide over the image, and it was trying to give the output feature and trying to find the pattern in the image. So this is the first and the initial step that takes place in a convolutional neural network. So is there any problem, or it's like, okay, it could be difficult. It's like I've tried to add and you don't need exactly the formula to get into that. But if you know the formula, it's well and good. It's the best thing you can know. Like you can get the intuition what is actually happening with the image before the data is being given into the model, and that is the most important part in the computer vision. So this is what actually convolution means. So moving on. So I've told you this is an image in which you can see over the time it's taking multiple different filters, and it's trying to classify the horizontal line. You can see it's even trying to classify all the edges in the image, or the what do you say, all the vertical lines. So this is the case for convolution. Moving on to padding. So for padding, I've added one more. Yeah. So once we have got our or if we have an input image, and in that input image we need to classify cat, and that cat's photo in the image is in the top right corner. But what our convolution does, it just slides over the image, and most probably it takes the whole image, but sometimes it misses the output if the image is in, or the feature or the information is in the corner. So it's like the probability of that feature being trained or learned is like less likely that it will be learned. So this is one of the drawbacks. Like we need to add padding to it. What is padding? We simply take an input image, we just increase the size of matrix, we just add either 0 or 1, so that it could slide through the image, and it could take that corner pattern is moved to the center by default. Since we add padding to it, this is what happens. It could be anything. It could be inside. If the feature is inside the image, it's good. But it could be in the end or the corner. So that and for this reason we use padding to increase the size of the image. So again, you can skip the maths part, not required. So since our image shrinks every time we perform convolution, we can do it only a limited number of times before our image disappears completely. So there's one more thing that I've missed. Over here you can look into this. Like what was initial our matrix size? 3, 6, 3, 7. Yeah, so it's 7 into 6. But after convolution operation is being done on the input image, the feature map is being shrink down. It's being converted into 4 into 4. So if we go down to, if we keep on doing this, at the end it will be a single, or it could diminish. It's like there will be nothing else to convolute to. So that is one more reason why we add padding to it, so that our image or the feature map does not become so small that even the computer is not able to understand what it is. So this is one more reason why we add padding. First we use, because if the feature is at the end of the image, like if the cat image is at the end, so for it to easily able to recognize it, we add padding and we try to shift that to the center. And secondly, we use it for the same reason, because after convolution operation takes place, the feature map is shrink down. So we add padding to help us in that situation. This is the formula for, so to solve both of these problems, we can pad our image with an additional border. For example, if we have 1x padding, like just adding one row and column to the matrix, we increase the size of our proto to 8 into 8 so that the output of the convolution with 3 into 3 filter will be 6 into 6 filter. So if we add 1, it will be converted from 3 to 3 to 6 to 6. So this is how we can increase the size of the image without adding any information to it, but still getting the desired output. And this is the formula where f is the filter dimension, and padding is like it's calculated using this formula. The next important part, what we have looked so far, is the convolution that takes place. At the end of this theory part, I'll just show you an animation in which everything will be clear. Just bear with me this maths stuff. So, strided convolution. We have looked into convolution operation, we have looked into padding. Now this is strided convolution. What we always shifted our kernel by 1 pixel. However, step length can be also treated by one of the convolution layer hyperparameter. The dimension of the output matrix that take into place. Okay, this is just theory stuff. Let's move into animation part. So initially, So initially, the shift was taking place at 1 block. Like it was going from 1 to 9, not 1 to 8. But now what stride does is it shifts the whole block by 2 strides, not 1 stride. This could increase the decrease the time complexity of the model and help the model to understand it better. So this is what stride is. Basically, the kernel is the filter. That is what it's helping to create the feature map. But stride is, instead of moving it and shifting it once, it's shifting it twice. So you can see the kernel, and sometimes it's better to get a feature map from 2 strides or 3 strides, and it gives better output in this. So this is one of the hyperparameter that is not compulsory, but that could be added if you want to. You can. This is a trial and error. This could be a trial and error method. You can try it according to your use. So this is what stride means in convolution. This is a formula that. Okay, we'll just skip the formula. But this is our input is images are still now in 1D. There's no 3D involved into it. But the same thing, what happens into 3D stride, we can look into it. So the only difference between 3D stride is it takes place into each and every layer, or each and every channel, where we could say. So it takes place into the R channel, B channel, and G channel. So the only difference between the only difference between 1D stride and 3D stride is that 1D stride it takes only in a single channel, but whereas in 3D stride it doesn't even just. The thing I wanted to say is like it takes place in each and every channel, not a single channel. It takes place in 3 different channels, 3 different convolution operations takes place. Then again we get an output matrix and the output feature. From that we can say, okay, we get a 3D or 3 channel output. So this is the only difference between 3D stride and 1D stride. Further, let's move to pooling layers. Besides convolution layers, CNNs very often use so-called pooling layers. They are used primarily to reduce the size of the tensor and speed up calculation. Tensor is nothing, just matrix. Tensor is another word for matrix. And for the max pool layer, we select the maximum value of each region and put it in the corresponding value in the output. So, for example, we got the input feature after applying the filter. We still want to reduce the size of that feature. So, how do we do that? We do that using the pooling layers. So, last but not least, if you are performing pooling for a multi-channel image, the pooling for each channel should be done separately. The same case for stride. This thing happens in the same way in pooling layers. So there's this. Yeah. So once we get that input, the pooling layer takes it shifts through the image through a matrix, and it takes the maximum of that. There is multiple types of pooling. It could be global average pooling, max pooling. over here max pooling is taking place. We can see it's taking the maximum of those 4 matrices. We can see like first 4 column and row, we can see that first 4 matrices, like 7 is the largest number in that. So this is max pooling, and this helps in feature recognition, this helps in feature extracting in a better method. So we can say that if there is an image and that 3 is less valuable than 7, so better than taking 3, 0, 5, 7 again as a convolution, first we can take 7 as our max or as our feature, then we can apply convolution operation again and again after that. So this is what pooling layer does. It takes the maximum, and this is an example of max pooling. Similarly, in average pooling, it takes the average of the whole matrix, then it gives the output. So till this point, is there any doubt or is there any question? Yeah. Information loss होती है. Like if you can look into this, maybe you don't know either. They are looking for dark images. 0 is being missed over here, and it's taking the brightest intensity over here. So this is also one of the trial and error method that you need to work on during building the model. We need to check whether it's giving a better accuracy during max pooling, average pooling. In that case, if that case, we can use average pooling. That will give us better output. Okay. So this is max pooling. So we can try to. Yeah, now these were the small features that were used in convolutional neural networks, but now we can try to combine that and look into the working of convolutional neural networks. I want you to once just look into it, or I'll just keep on. So over here, what it's taking place is the filter. It's shifting. For us, it's we can easily recognize that's a. But in this, we can see the filter. It keeps on moving on the image, and it's trying to find the pattern. And it's trying over here. You can see it's looking. So the green one is the intensity from dark to light, and the red one you can see it's trying to find the pattern from light to dark. So red is the negative, green is the positive, which it has found. Similarly, again a different filter is being applied to the image, and that is again taking place using shifting convolution operation is taking place over here. And again it's trying to find the pattern from A. Like what is happening in A, like it's trying to find giving the mathematical or numbers to it. Like red is the negative one and green is the positive one. So over here we can look at the use of ReLU. Yesterday we learned in depth like what is ReLU, what is the activation function. What over here ReLU does is it removes the negative number, because we don't need a negative number. We need only from 0 to positive 1. So it removes the red from there. Again that same convolution takes place. It finds from that. Let me just go back. I'll just explain. 1 second. It's better. Yeah. At this part, again, it's what we can see is a pooling or something happen. Pooling layer is taking place. Now again, that two outputs are being concatenated to each other, and then again feature extraction. Again the convolution operation is taking place, and again feature extraction is happening over here. Now again those same filters are being applied, and at the end what it's trying to find is the pattern from the input image. It's trying to find, and now it matches with the given output, like what is the probability that it could be, like A, B, C, D. If the pattern matches like with 92% confidence and 92% probability, it could say like, okay, it matches with A, so the image is A given to us. So I hope from this animation it would be clear how this convolution pooling, I've skipped the pooling part and styles part because it's difficult, but in this animation, hopefully you could understand how convolution takes place and how this activation is working, ReLU. So, is it clear to everyone, or should I replay this again? Okay, so should we move on? Replay? Okay, yeah. Okay, no issue. Like it's trying to find those like patterns. It's trying to understand. Okay, over here we can see it's trying to find horizontal patterns. It can look into, okay, the intensities is being changed from white to dark to white, and since if it goes to dark to white, it can see, okay, there's something that we need to learn. So it's giving the output in green, but after that it's being shifted to black. Like as soon as it is moving, it's being shifted to black, and from that it's being changed. The color is being changed to red, and at the end we'll change that, at the end we'll drop those negative numbers since we don't need that, and that's useless. And we use and we can do that using the ReLU activation function applied to it. So again, the feature extraction part is taking place. This is the second part, that again convolution is taking place at the second time. Now again the features, again the negative numbers are dropped, and again the convolution output is being concatenated to each other, and the pattern tries to match from A, B, C, D. It's like, okay, it's not 100% correct, but okay, 92% confidence, it could easily say that it is A. Not A, B, C, D. It is somewhat trying to correlate with A, but that also for 2%. So it knows, okay, it's not true, but it has similarity. So this is the working of convolution neural network, not like actually convolution operation taking place. So we can combine what we have learned till now, like pooling layer, convolution layer, and we can try to build an architecture from it. We can try to build multiple different architectures. We can leverage those advantages that are being brought by pooling layers, trides. But one of the famous, these are some of the famous, and like the first convolution neural network, this was LaneNet 5. It was built in 1998, and this is one of the simplest architectures. And it has only 2 convolutional layers and 3 fully connected layers. Okay, after this convolution pooling takes place, we are given a matrix output. But yesterday I have given you an example where we need to convert it into a 1D vector. So most of you okay, let me just repeat it again. Okay, you are given a 2D matrix. Since we need to convert it, we usually convert it into 1D vector. That makes it easier to create these neurons and connect each other to further down the line. So this is why we just convert it into 1D vector. So this is what 3 fully connected layers means. Fully connected means it is connected to, each perceptron is connected to the next hidden layer with another perceptron. So further, AlexNet, it had 60 million parameters, and AlexNet has 5 layers, 5 convolutional layers, and 3 fully connected layers. AlexNet just stacked a few more layers onto LaneNet. And you can imagine that this thing is happening in 1998. Actually, computer vision is long before it took place in 1960, but that was in few small bits. It's like not proper foundation was being built, but proper CNN foundation was built by LaneNet. I have one of the video where it actually took place. I'll just show you after this. So next is VGG16, which was built in 2014. It has 13 convolutional and 3 fully connected layers. Carries with them ReLU tradition from AlexNet. So these are like the modification of the previous architectures that were state of the art. So LaneNet was at that time state of the art, but someone got the idea, okay, let's stack 2-3 more convolution layers to it, and it gave better accuracy than LaneNet. in similar format, VGG16 just modified a bit, and it has 138 million parameters. What this parameter mean is the connection that it has. It's the connection that is being, it's 138 million connections that it has in each other. Like in our brain, we have neurons. In our brain, we have, similar to neurons, the connection with each neuron. This is 138 million parameter. So we can look into the its architecture over here. Yeah. So these are the architectures that take place. So let me explain first by LeNet. A 32 into 32 image was given to it. A convolution operation was taken place, which was 5 into 5, the size of the convolution filter that took place. After that, average pooling was used in LeNet. I told you what is average pooling. It is the matrix sum, like this average of the matrix that it's being taken from the input image and given to the output image. So this is the architecture of LeNet. It's basically a stack of input image, convolution image, like convolution operation, pooling layer, again convolution, again pooling, then finally being connected to the fully connected layer. Fully connected layer, you can see over here, I've given an example, like it tries to just narrow down those neurons into what you are required, like what we need as an our input. So LeNet 5 follows this architecture, and over there you are seeing, like in yellow it's written T, S, R, and R. It's R is mostly written over there. So these are the activation functions that were being used. In the animation we saw ReLU was being used because the negative numbers were being dropped from it. So this is the architecture of LeNet. Similarly, what you can see, the difference was only in activation function. Instead of tan T is the tan function, activation function that was being used. And in AlexNet, our ReLU function was as our activation function was used, and only one more layer of, three more layer of convolution operation was there, taken place in this. Further down the line in VGG16, you can see, if you can see at the bottom, it's written into 2 into 3. So the same architecture was again like just added to the stack. That is how just it's being generated. Like the architectures are being built. And at the end, after this 1000, like at the end, the softmax activation was used, in which it was maybe at that time input was so input was 32 into 32 image. The output was to classify between 1 to 10, which was digit recognition. Now I'll show you like the author of this paper was Lei Yakun. He is like one of the brilliant mind, and he won a Turing Award for this thing. And he is like one of the pioneer in this field of computer vision. And he shared his video from 1998 for the first time how computer vision and CNN is working. So maybe 1 second. Okay, that's on my computer. Okay, at the end of this, I'll show like videos that I have. So further moving on, what can computer vision do? Like, okay, we have learned so far how does it work, how is it working, and how does it how does it understand what an input image is, and how it manipulates those input image according to its rules. But what can computer vision do? And these are some of the major techniques that are being used. First is object classification. Object classification, it assigns object in an image to a predefined class. Yesterday we did a hands-on session in which we tried to classify. What did we try to classify? We did MNIST. We did it on MNIST dataset, in which we tried to classify in between different style and dressing clothes. So this is what object classification is. If you are given from 0 to 9 digit, you need to classify what a 0 is, what a 9 is, what a 5 is. Further, object localization. Locates an object in an image by enclosing it in a bounding box. So there's an image given to you, but there's a cat sitting in that image. So you need to give a bounding box to the image. Object detection, it detects an image and it gives the label and localize it. It does both. If a cat is there in an image, it will create an enclosing box near the cat and it will give a label cat to it. Semantic segmentation, it understands every pixel of an image and associates it with a class label. So there are multiple classes that could be taking place, but it could just draw color. It would make a colorful cat. I'll just show you in the next slide the examples of it. Instant segmentation, that does semantic segmentation, but it individually identify each and every each and every object differently. In the next slide, you can see. So this is what I was talking about. You can see from this, it is able to understand what a cat is, and like this is a classification problem. It's just able to classify what a cat is. Further, this is semantic segmentation, in which it is giving color to each and every pixel. Like what a cat is, what a grass, tree, sky with different. The same image is used, but the pixels are being changed for better visualization. This is what semantic segmentation do. Object detection, it classify and detects each and every object in that image. Similarly, instance segmentation, which identifies and change each and every pixel in that image of different classes. So this is what computer vision basically, what can computer vision do? So we can look into some of the applications of computer vision. This is like what we can look into it. So these are some of the recent applications that are being used. One is firstly image recognition, healthcare, agriculture, military, self-driving car, manufacturing. Image recognition, everyone knows what a face unlock is. Most of you have iOS. Those who have iOS know what a Face ID is. So how does Face ID understand it's you? So it tries to, like at first you need to register your image in it, and from that image it learns, okay, it learns the feature from your face, and the next time when you open it using Face ID, it does it in an instance. So it does not take any time. So this is what image recognition is. There could be multiple things, recognizing difference between apple and orange. This is one of the applications that. Secondly, it's healthcare. Nowadays, more healthcare is shifting towards and utilizing computer vision. How is it utilizing? Many we can look into many MRIs and X-rays, in which some of the data has shown AI has surpassed radiologists who are like professional in finding and looking into X-ray, but AI has surpassed it by looking into minor fractures or major fracture, which was overlooked by the radiologists and pathologists in that. So in that sector also, in healthcare, it is working very good. And moving on, agriculture, it could be any, agriculture is like, nowadays in agriculture, drone is being used for planting seeds and all. It could be used to help, it could be used in counting trees, like number of orange trees available in that. And from that, in that perspective, computer vision can be used. Further, in military, in military, it's like from understanding military, it's like it can be used in surveillance, human recognition or face recognition to recognize any known known prisoner or known assailant or something. Self-driving cars, everyone know what Tesla is, or everyone knows what self-driving car is. It's like the future. Self-driving car uses it uses computer vision to understand its locality, its surrounding and its environment, and from that it's able to drive from its own. It's not taking any other method other than computer vision. So moving on to manufacturing. Nowadays manufacturing has totally been moved, like there are many factories in US that have been fully automated. It depends now on an AI and a manufacturing arm and robotic arms to make those products and help them in manufacturing. So over here, how does an robotic arm look into or identify an object? This is also one of the good application of computer vision, which is manufacturing. So this is from my side. This is like if you have at this point, if you have any other question or any doubt regarding computer vision. If not, I have some videos, like cool videos. If you want to look like how you can build the what do you say, LayNet and all, like advancement of computer vision that I felt like it would be good to share. So I'll just share those, and after that we can have. So let me just share. So this was one of the this is a video from 1998. At that time, like this is the first experiment on LayNet that I have given an example for. It's Lei Yukon who was sitting over there, and this is the first OCR, basically digit recognition, that is taking place. You can see like how it's being easily able to recognize the digits at that time in 1998. So it's like any handwritten, that also not proper printed image, but handwritten. It's able to classify handwritten images with 99% accuracy at that time. So this was one of the what could you say? This could be like one of the breakthrough at that time in the field of computer vision. This one and there have been many advancements, and there's one more thing that I would like to share. It's recent advancement of computer vision. Like nowadays, you don't even need to give context to it. It's like, I'll give you a real example. If like, are you bored or should I continue? Like, there's some cool stuff to show. Like, I'll just show you. Like, okay, how many of you know what DALI is? DALI, you know what a DALI is, right? So basically, you are giving a prompt to the computer, and it's able to generate image, video without any other human intervention. It's just trying to understand the context of that text, and it's trying to generate its own image. So basically, this is one of the video that was generated by DALI without any human intervention. And this could be a bit creepy, I don't know, but like, I'll tell you the context. The only single line it was given was future, or like how did human evolution take place. This was without any human intervention. This was the output given by the computer. So you can look, it's not perfect, but you can understand the context, how computer vision and how computer is trying to understand from it. Like, how did this evolution take place? And it shows the future, like how does this future, what will we look like? And this is totally generated by computer with no human intervention. I know at the end it becomes a bit creepy and this thing, but this is what computer understands. Like, this is what computer thinks that our evolution will look like without any human intervention. Similarly, this is the last video that I would like to show. This was another given, like the voyage of whole planet, what whole planet looked like, and how did evolution begin in the planet. So this was multiple sentences was given to it, and this is what it generated, a 1 minute video without any human intervention. Again, this was totally generated by computer. understand anything, but overall context given by the computer is what is the main thing it is trying to convey to us. And the best part is it's 100% generated. Like it's learning from internet and the training that it was given. This is what it was able to generate.